Okay, everyone, can you hear me?
Yeah. Yes.
Yes. Okay, everyone. So it is live now on YouTube. So everyone, just as continuing the program, developed it and presented by Kevin Pacheco, who is an instructor here at Harvard Medical School, Department of Physical Medicine and Rehabilitation. uh, and also a scientist in the Spaulding Neuromodulation laboratory. So we'll continue now with the stats bit, which is the basis to learning statistics. And today is the third lecture, and with the basis for understanding more the statistics. We look forward. Thank you very much, Kevin.
Today we're gonna start with the second part of probability. So the idea, it was in the previous session to understand the basic nomenclature, the basic words and definitions, and we discussed a little bit of how we conceptualize probability from a frequentist approach, like counting and divided the numerator divided by the denominator of the total sample, and so on. So the thing is like that is not enough. That you will use only on, let's say, physics or mathematical simulation, because every time we are doing a clinical research, we are actually facing with conditional probabilities, right? Because we are not assessing one dimension only. We always have data that is multidimensional. We always are interested on more than one variable, meaning more than one event it's happening. And when we are analyzing the data, it's impossible to isolate events, right? If one outcome is it's happening, also at the same time, other things are happening. So when we are dealing with any type of modeling, we need to consider conditional probabilities, right? So in order to understand what is a conditional probability, we need to start defining what is marginal and what is joint probability, because conditional is a special type of combining joint and marginal probability. So the best way to do it is with an example. So let's start with a quick example using a Venn diagram. And let's use a very common scenario that we have in one of our trials, that actually Mustafa, Daniela, and Maria Fernanda are going to this clinic, to the amputees clinic in the Spaulding Rehabilitation Hospital. Let's say in a specific day, this last Wednesday at 11 a.m. Okay, so basically when we are there, we are trying to define some events, right? One of the most important, of course, is the PLP, right? So let's call the variable A, which is, oh, sorry, the variable Y, should be Y actually, that is the presence of PLP. So this will be a binary event, which you have two levels, yes and no. So one will be yes, zero is no. And then we have another event at the same time that could happen, because they are not mutually exclusive, they could happen at the same time, is another variable that is called the phantom limb sensation, right? Those two are different variables that are actually part of a phantom limb experience. One is painful and the other one is non-painful. And let's say in total, we have two patients that day that have PLP and have PLS, right? And then we have also 4 patients that only have PLP but not PLS, and then 5 patients that have only PLS and non-PLP. And then we have 3 of them without any phantom experience, right? So this is a classic setup. I'm sure you remember from your high school, right? It's just basic set theorem. And then we have the total numbers here written with the correct notation, which is, y should be actually y, the PLP, equal to 6, because we are including both of them, right? We are including this part and also the intersection. That's why it's 6. And then the A, which is PLS, level 1, which is they have PLS, it's 5 plus 2, so it's 7. The intersection is 2, and the universe, in this case, all the patients that they saw in the clinic, it's 14. Okay, that is classic Venn diagram of a scenario with two events that are not mutually exclusive. So then you could represent this scenario with also a different technique, which is called a contingency table. This contingency table is going to present the same numbers, but in a more organized way and easy to calculate some statistical tests. So just to confirm that you understood that, can you tell me, for instance, what will be here in this initial cell, which is the number, because we are counting. But remember, we always start statistics and probabilities by counting, right? So let's count the cells that are here. So which number you will put here?
5.
It's 2.
It's 2.
It's 2, right? Because you are asking here the patients with PLP and PLS. So will be the intersection that is these 2, right? Then the other cell here that is no PLP but PLS, which number will be?
5.
5, right? Because you want patients with only PLS that are here in this part of the diagram. Then in the other cell, you have patients with PLP, but not PLS. So which number will be? 4, right? And then the other one is patients with no PLP and no PLS at all. 3, right? So you see, it's very simple. It's the equivalent. You could represent the same scenario with Venn diagrams or with contingency tables. Usually in statistics, we like to use contingency tables a lot for different statistical tests. And then let me just show you the numbers that you just said. And then we can count the margins of the table, which is the total sum of events, right? The 2 plus 5, the 4 plus 3, and so on. So this is very important because when we are saying margins, we are referring to the total of both the rows and the columns, okay? So now, let's say, in this case, I don't know who is in the clinic. Let's say it's Mustafa and Maria Fernanda, and they are waiting for the next patient, and one of them asks to the other, right? I bet you $1 that the next patient that we see has PLP and PLS, right? So they have the data of the whole day until 11 a.m. And now they are expecting the next patient, and they have this statement, which at the end, as we discussed last time, we could express as a probability, right? So now let's use this table to calculate that probability of having the next patient with PLP and PLS. So remember the notation we discussed last time? We have probability of y equal 1, which is PLP, presence of PLP, and A equal 1, which is presence of PLS, right? So now, what would be the probability based on that table?
2 over 14, 1 over 7.
2
over 14.
Over 14, right? Because we have this initial cell, which is the patients that have PLP and PLS, and the total number, which is 14, right? So then you will have 2 divided by 14, which is 0.14. So that is the example that we could use this table to calculate probabilities according to the combination of those variables. So that's why at the end, a contingency table can be completed with probabilities of all these combinations. So let's say we have PLP, which is y equal 1, not PLP, which is y equals 0, and PLS, which is a equal 1, and non-PLS, which is a equals 0, right? So then we could just count and then divided everything by 14 because it's the total, right? When you consider the whole 14, we are talking about the unconditional probabilities. So all those values that we calculate there, we call it unconditional, okay? Why? Because we consider the whole universe, in this case, the 14 patients of that amputee clinic. So then we have 2 different subtypes of unconditional probabilities. The marginal probabilities, which is actually, as the name says, the margins of the table, right? Which is this 2 totals and the other 2 totals. And then we always use this 14 as the sum of both, right? And that's why we call marginal probabilities. This is very important because we use the margins in a lot of models. When we calculate the margins in a regression model, in ANOVA, we are talking about this marginal probability, which is considering the events A equal 1 or A equals 0 or Y equal 1, Y equals 0 isolated, right, over the total population. But also we could have joint probabilities, which is the intersections. When you combine A equal 1 and Y equal 1, or A equal 1 and Y equals 0, which is all this center here. You see? So then at the end, sometimes we need joint probabilities when we are interested in combination of events, but most of the times in the classic clinical trial analysis, we are interested in marginal probabilities, okay? But if you put all together, you are talking about unconditional probabilities. This is important when you are only doing pure clinical trial analysis, because you are assuming that randomization will clean all the confounding. So then you can consider that A and the treatment 1 and the treatment 0 will be completely equivalent or exchangeable, and then you can just work with marginal probabilities. But most of the times, even in our trials, we need to adjust by something. So when you are adjusting by something, you are actually conditioning on the variable that you are adjusting. So we always work with conditional probability. So let me show you now, first, before we move to the conditional, how you represent the same idea with Venn diagrams. Okay, so this is the marginal probability of Y equal 1, which is presence of PLP, and reads the, in that way, the probability that Y is equal 1. And then you have this classic Venn diagram. This is with different numbers, but it's the total A divided by the total 20, which is the universe, right? Then let's say we calculate now the A equal 1, which is the PLS, and it's the same idea, right? Just in this case, you need to visualize the whole set of Y equal 1, and then the whole set of A equal 1 divided by 20 in this specific example. Then now let's do the Y equals 0 and A equals 0, right? So that's a little bit more complicated. The Y equals 0 would be, you know, the 12 that you have, because it's all the numbers that are outside the Y set, right? Divided by the total, which is 20. And then you could calculate the A equals 0, which is the same idea, is the complement, right? That's why you could just use 1 minus the probability of A equal 1, because it's the complement on the set, right? So this is just how to visualize the marginal probability, which is usually very useful for the conditional. And now let's see how we do this for joint probabilities. In this case, it's even easier when it's Y equal 1 and A equal 1, because it's literally the intersection divided by the total, which is 20. But the things get a little bit tricky when you start combining levels. When you start combining Y equal 1, which is PLP, and A equals 0, which is not PLS, right? So then it's 6, because Y equal 1, it's all this whole set, right? 1 equal 1, but no PLS. That means you subtract those two that are in the center, so you get with only 6. 6 divided by the total population, which is 20. You see? So at the end, you could start combining not only the presence of that event, but also the absence of that event. That's why you could have Y equal 1, A equals 0, or vice versa, okay? Then this is about joint probabilities. And now, to understand the conditional probabilities, let's add an extra statement, right? Let's say in this scenario, you are waiting for the next patient. And in this case, Dr. Crandell, who is part of the clinic, as you know, tells you, oh, I know this patient. And in the past, he told me like he has PLS. So now you have an extra piece of information that the patient that is coming, it has PLS. So now what is the probability that this next patient also, on top of having PLS, also has PLP. You see, that is the classic statement of conditional probability, which reads in this way. We need to use this notation, this vertical line, and then you have two segments now. You have the probability of y equal 1 given then a is equal 1. You see? And then you just read it in this way, the probability of y equal 1 given a is equal 1. And then that sometimes is confusing because there is something missing there that I would like to put it in words and then in notation, which is a bit redundant, but it helps you a lot to understand the concept. So now let's put it in this way. Is the probability of having PLP and PLS among those patients that we know have PLS. So actually the numerator is not only y equal 1, is y equal 1 and a equal 1, given you know a equal 1. So that means we could write this down in this more redundant way, in this way. So you have the a equal 1 in both the left side of the vertical line and the right side of the vertical line. So then it's easier to see. Let's do it now with the contingency table. So now you have this scenario. Instead of having the 14, which is the total number of the population, you first start restricting your population to this right side of the vertical line. This a equal 1, now you know is 7. So now the denominator will be 7 instead of 14, right? And now you know that the other part, the left side of the vertical line, is the number of people that has y equal 1 and a equal 1, which is 2, right? So now you just divide, which is 2 divided by 7, and now it's 0.29. So this is very important because if you are not careful, you can think like this 0.14 is the same, right? And there's like a lot of confusion, but actually the vertical line implies that you are restricting your denominator to that given information. So that's why, if you can see, the probability of the next patient having PLP, knowing that has PLS, is larger. It's 30%, almost 30%. It's the double, right? So that's why at the end, it gets tricky when you start restricting to different subpopulations. And then this is the complement of that, which is what is a probability that the next patient has not PLP, right? Which is y equals 0 and a equal 1, given a equal 1, which is 0.71 because it's 1 minus 0.29. You see, so then both are complement and both are different than the classic joint probabilities. So they are not the same, and that's a very, very common confusion. Then now there is an interesting property here that helps you to understand as well how we use this. So the property is like you could calculate conditional probabilities from unconditional probabilities. Let's do an example. So for instance, we know that we just calculate this conditional probability, right? So now what you could do is just to replace this, instead of having 2 divided by 7, you will have 2 over 14 divided by 7 over 14, which is actually the joint probability divided by the marginal probability. You see? So you are using the probability of PLP and PLS divided by the probability of PLS, which is the marginal, which is this one, 7 divided by 14. And at the end, they are equivalent. So it doesn't matter. You could use the count or you could use the unconditional probabilities if they are available. But why this is important? Because not all the time, I would say almost never, you have the whole contingency table. You always collect one part, right? Some of the cells. And the idea is like you need to calculate conditional or unconditional depending on the data that you observe. So that's why these relationships between probabilities are very useful and are actually the base of the Bayesian theorem. So that we discussed last time, remember. So now with all this background, we are gonna learn how to interpret the Bayesian theorem next session. But just to formalize this is the formula that we have in all the textbooks, right? The problem with the classic textbook is like they give you the formula first, and then you get scared, right? And then give you the example. But now, if you go from the examples, then you will realize that the formula, it's obvious, right? And at the end, that's how they did it, right? That's how Bayes and Ben, which is the one that invented the Venn diagrams, they end up with these relationships. So at the end, in conclusion, when you have a conditional probability, you need to know the intersection, the probability of the intersection divided by the probability of the information that you know, right? Because you always know the denominator. That's why it's a given, right, that you receive from the statement. And at the end, you can represent this using, row counts or unconditional probabilities, which require the joint and the marginal to calculate the conditional. And you can represent this also with I think it's loading, with a Venn diagram as well, right? Which is first, I always like to think first on this right side. So first you stratify the second set, right? So then you know you are working only with 4, right? Because it's given a equal 1. And then you move to the left side of the vertical line, which is y equal 1, within this subset of 4. The one this second, the right side, right, of this diagram. And then you will have 2 divided by 4. You see, so always you can consider the conditional probability as a subgroup probability, right, or a stratified probability. And interesting enough, when we are doing adjustment in regressions, we are using this principle. We are calculating probabilities in subgroups, especially when your confounders are binary. And then we use that to calculate an adjusted new probability using this joint and marginal. And we're going to see that examples afterwards. But the idea is that with this information, now we can understand the Bayes theorem, which is part of this Bayesian statistic that we discussed last time. And then especially to understand, like, knowing one part of the cells of the contingency table, we can calculate the rest. We need only 2 pieces of information from the table. And then with all these relationships, you could figure it out the whole contingency table. And then, but you notice that we are using only binary outcomes, right? Because it's easier. But what happens if we are considering continuous? And then is when we need the distributions, because we're going to do the same thing, but instead of measuring one value, we're going to measure an area under the curve. But the same relationships also hold, right? It's just changing the way we calculate this specific probability. Now it's at a point but we could use an area under the curve. Okay, so any question about these different types, the joint, the marginal, and the conditional probability? No? I hope it's clear. I know it's something that you have the intuition of, probably related to your high school or your med school mathematics courses, but actually most of the biostatistical textbooks are not really presenting this and how you connect with your data analysis task. So I think it's very, very useful. Okay, so if we don't have any question, let me see in the chat. We can stop the recording now, but Professor, any question? Probably not.
Prof,
Let's see if Prof is connected.
I think it's good.
Yeah, if not, I think next I don't know if next week, let's try to do next week. We're gonna cover those two topics, right? And then the plan is to start, as I mentioned, building a house, right, with these small pieces of information. And then you will see at the end, everything makes sense. It is completely logical, you know, the whole, at least the frequency statistics, which is the one that got a lot of attention because of that, especially. Yes, there was any question or
Yeah, no. I
comments?
think that was wonderful, Kevin. So I think I was just a quick thing for the group as well. So I think this was a great example, and especially so I think probability is in the universe, and that's your basics. Go to your basics, high school. What's greater? What's the denominator? Relation sometimes what gets you guys confused, but then you start seeing more examples, things become much easier because it's interesting. So when I took my biostats and epic courses at the School of Health, probability of y given probability of y equal 1 given the x equal to 1, it gets confused when it goes notation because your brain is not used to the language. It's all about the language.
Oh, I think we lost Professor.
Hello, did I lose you guys?
Oh yeah,
did I lose you?
He's back. Yeah,
okay,
yeah.
So I don't know. Yeah. So, hello, can you hear me?
Yeah, no, yes, go ahead. Yeah.
Yeah. So no, I was just explaining. Again, the whole thing is understanding the language. Again, when probability of y equal 1 given the x equal 1, so your brains are used to that language. And when you get used to the language, and you only get used to the language as you practice. Same thing as when you learn the English language, if you're not a native speaker, that's now your brain automatically understands that. You don't need to think before you speak. So that's what you need to train a little bit more, so then you understand the statistics, the language of statistics in an easier way. I think that's part of learning, and that's why I think going back it helps you. Otherwise, you get from the middle, and it's very hard for a brain getting from the middle. That's why this is so important. And hopefully when you understood everything. But then if Kevin comes here and he starts explaining, so when he explained a little bit of Bayesian analysis, showing probabilities, conditional probability, and so on, it was very confusing for you. Why? Because your brain did not have this language. Okay, so I think that's an important take-home message. Very good, Kevin. I think that's all. If no other questions, Happy New Year, everyone. And exactly, yeah, so claps to, where's my clap here? My emoji of claps, I can't find it here. I think this one, yes. Thank you so much, Kevin. It was a wonderful program. And then, yes, guys, Happy New Year, everyone. So looking forward to 2024. It'll be a great year. I'm 100% certain of that. So the lab now is moving super fast. We have a wonderful group. We'll have more papers, more grants, more trials, more everything, and more learning, especially. Okay. With that said, everyone, I look forward to seeing you very soon. And if you need anything, please let me know. And enjoy your New Year's evening. Thank you all.
Thank you.
Professor.
Thank you, Professor.
Bye-bye.
Bye.
Happy New Year's. All.
Happy New Year, guys. Bye.
It's connected.